Good. You should look at what's written on the board. Don't look at me. So one month ago, I had the experience of giving a lecture at MSRI that was on video camera. And then afterwards I looked at the picture and all you can see is the back of my head. So it's very stupid. If you're in a television studio, then you have makeup artists and so on. And they look at you look at the face. Approximately 30 hours each. So this is the first course. The first is July. That's now to September 2009, and the second will be January to March 2010. So that's already fixed, and then 2011, 2012. I don't know exactly the time, but there may be similar times. So in the later courses, I will talk about my research specialities. Classification of varieties, algebraic surfaces, algebraic threefolds, classification of varieties. But this is the first lecture course, and I want to start at a fairly basic, low level. So so this is at a fairly basic level in algebraic geometry. So Professor Lee Yong Nam told me that students from Sogang and also the neighboring universities that are partnered with it, Yonsei and Yihua, can take the course for exam. So undergraduate course for credit, this means for exam. So could you show your hands if you intend to take the course for credit, or you're thinking about taking the course for credit? 3 or 4? Not very many. Can you maybe translate what I said? Maybe not so many, 6 or 8. Mm-hmm. So I think I will try to make the assessments, the exercises and the exams as easy as possible so that students who make a little effort can get good marks. So as some of you probably know, I have this textbook, and I will not follow the textbook, but the syllabus of the course is more or less what's in this book. So do people have copies of this? How many? Are the people here who don't have any copy of this, don't have access to a copy? That means everybody has a copy. Maybe I should ask the question the other way around. Does everybody have a copy? Okay. Okay, well, so I bought 3 or 4 if people need it. So from next week, maybe we can circulate copies of a first graduate course that I wrote some years ago. Okay, so as I say, this is really basic, introductory level, first level into algebraic geometry. So I want to say some of the students here will be very clever and will understand everything I say, both in mathematics and in English. But the course is not only for the very smart, the very clever kids, students. So if there are things you don't understand in mathematics or in English, please tell me. Please ask questions. Please interrupt the lecture. Or you can ask me to speak more slowly. Or I can sometimes give translations into Korean of technical terms, because I know how to use the Yahoo online Korean dictionary. Or if you have other questions, you can send questions to me by email at So if you ask me questions, if there are things you don't understand, then I can try to put that right in the lectures. So in other words, students, it happens to me when I lecture at Warwick that some of the students who come to the course are third-year undergraduate students, so basically beginners who don't know a lot of algebra, don't know a lot of the other subjects, and I want to make the course accessible to students who are not already PhD students.
So, is it a comma between minus and?
Dot. Thank you. So on the other hand, there are some students here who are much more advanced, and for whom this course will be, coming to the lectures will be rather boring. So I should say even elementary material can be interesting. And so I propose a graduate seminar. So this is a suggestion. I won't organize it myself, but I suggest a graduate seminar, possibly Tuesday and Thursday. Maybe if it's, for example, at 11 o'clock. So where graduate students can read some books. So I have notes of I propose that good sources would be to study Jean-Pierre Serre, faisceau algébrique cohérent. So this is a very important paper, 1955. It is a lot easier to read than Hartshorne, and it's of course the material that Hartshorne copied. The only disadvantage is that the paper is in French, and some of you may have difficulty reading French. So anyway, this is a suggestion. Alternatives, there's David Mumford's book on abelian varieties. There's my Park City chapters. And there's quite a lot of other material that, for example, Professor Young Nam can tell you about. So, for example, I notice he has on his desk the little book by Arnaud Beauville called Complex Algebraic Surfaces, which is probably quite suitable for students who want to get into not, the definitions and so on, but the actual material of study. So as I said, I hope that we can make these chapters of mine available to you. We can print out copies for anybody who needs them. Okay. So to run a graduate seminar, you need a volunteer to make a mailing list, to do the organizing. So I looked at the dictionary for volunteer. I got Jawanja, and then I looked up what I really meant, and I found the word Pong, which it means fall guy, or the person who's going to have to do all the work. So, I think Yongju can organize this. But in any case, students who want to take part in a seminar like this, to study material at a higher level, you have to do all the work yourself. I can give advice, but I can't do the work for you. And you have to organize yourself. You have to decide on the times and who's going to give the lectures. So in particular, if that's going to happen, then somebody has to volunteer to give the first, maybe the first lectures in the first week or two. Okay. So that's the, so to speak, organizational stuff. So I'm going to start by talking about projective space, Pn, so especially P2 and P1, but other values of n, you can take n to be anything you like. So I'm going to talk about this, and I want to say why I'm doing this. So first of all, what is this? What is it? So I'm sure most of you will know the definitions. So let me say K is a field. So let K be a field. So could I ask, of the students here, how many students have done a course in Galois theory? Coursin-Galois theory, field extensions? None. Or maybe people are just not very good at showing hands. Yeah, have students who have done a course in Galois theory, who know what, for example, an algebraic field extension means, could you raise your hand? Absolutely none. 3 or 4. Hey, we're not doing very well. Okay, so I mean, this K a field. So we're doing geometry. So the usual fallback position is that K is C, the complex numbers. Right, but other possibilities are perfectly good. For example, I could take K equals R, or even K equals Q. So this would still give geometry, but it gives geometry which is basically harder than than over the complex numbers. So complex numbers are just easier for my purpose. So so if you're a number theorist, then you're not at all interested in the complex numbers. You're interested in the rational numbers or even in integers. Okay, so let K be a field, then projective space Pn is, I'm going to take K to the n plus 1, so you know this is x0 up to xn, take away the origin, and then divide out by an equivalence relation, where the equivalent, so this is an equivalence relation, which is okay, where x0 up to xn twiddles x0 primed up to xn primed. So in English, this thing is called twiddles. Right, it means the left-hand side twiddles the right-hand side. So transitive verb. Right, if and only if there exists a lambda in the field K, not 0. This is the multiplicative group of the field, such that x0 primed up to xn primed equals lambda times x0 up to xn. Okay, so we can say this in lots of different ways. So this is the same thing as ratios x0, x1, xn. So where this dot is ratio, P-ray. Okay, so this is just the same thing. What a ratio means is, in order for the ratio to be defined, one of these guys has to be non-zero. So this means that one of the xi is not 0. Right, and that's the same as removing the origin from this space. And then you don't care about the actual values of the numbers. You don't care about what these numbers themselves are. You only care about the ratio between them. So the ratio between them is exactly the thing that's preserved by this equivalence. Right? Or this is the same thing as the set of one-dimensional one-dimensional vector subspaces of V equals Kn plus 1. Right. So a one-dimensional vector subspace means I've got to have a non-zero element in there. To be one-dimensional, it's got to have one basis element. And then when I've chosen one basis element, all the other elements are just multiples of it. So that's saying exactly the same thing as this. Okay? So that's a definition. I've told you what it is. On the other hand, I'm not at all, this doesn't, this is a strange construction, and if you haven't seen it before, it's completely unfamiliar and unintuitive. So let me make some remarks. And this is really to do with why. So in other words, why I want to talk about projective space at the beginning of a course. So remarks 1, it's unfamiliar. If you haven't done algebraic geometry, you haven't done this branch of geometry, then you haven't seen this before. And it's unintuitive. So this word doesn't exist in the Yahoo online dictionary. So I made up my own translation. Jikwanjon Anira. Jikwanjon, anyway, maybe I'll write it out. In fact, I haven't got my glasses, so I can't read it out. So intuition is something you can understand immediately. You just look at it and you see it, jikwan, and unintuitive means it's not like that at all. So it takes some time to get used to it. And the strange thing is, I want to say this is n-dimensional. So this is n-dimensional space, but I need n plus 1 coordinates. Right, so these guys, x0 up to xn, are called homogeneous coordinates. Okay, so another thing that's confusing, another thing that's hard about this notion is that I write down these x0 up to xn and I say there's some kind of coordinates on the projective space, but they're not functions on the projective space. These x0 up to xn are functions up here on this space, and the projective space is this space divided by an equivalence relation. So what value of, for example, x0 I get depends on the particular representative of this equivalence class that I took. So none of this is very difficult, but it is unintuitive. Okay, so that's the sort of negative part. So projective geometry is central to algebraic geometry. So I hope that we'll come to understand this as we go in the course, This is not, I can't say immediately why this is the case, and even after 40 years studying the subject, I still wonder about this. Why on earth do we always work in projective space rather than some other space? But for example, e.g., when you study curves, algebraic curves, then you take your curve C, and the first thing you want to do with it is embed it as a closed subvariety in Pn for some n. And this is called the Riemann-Roch problem, and it's one of the is one of the main things that they started understanding how to do in the 19th century. So this is really a completely fundamental thing. If you do algebraic geometry, then most of it is projective geometry. And nobody can explain exactly why it must be projective geometry, but it just is. Okay, so let me say what this does. This gives it gives compact for free. So if I I'm going to start on real examples in just a minute. If we're not in projective space, if we're in ordinary space Kn, then it's like taking a curve, an algebraic curve, for example. It might look like this, and then missing out some number of points. So forgetting some number of points. And you know, if I take this picture here, Riemann surface, and I omit some of the points, I get something which is not compact. I get something where the field of functions, the functions which are regular here, is infinite dimensional. And so we just do this thing here. We say we're going to work in projective space, and we get compact for free, and we get lots of results saying that some vector spaces are finite dimensional, also for free. Right? So we have to do this. If you're going to do algebraic geometry, then you should do projective geometry. So 3. So I said it's not, I said it's not something you have already seen before. It's not something you can understand very, very easily. But this is really very easy. When I start explaining it better, this is really very easy. And also, it's also very effective. So, if you're a grown-up mathematician, then, you have an equivalence relation and so on. So, when you're in primary school, you learn what rational numbers are, and rational numbers are an equivalence class. And so you don't, we're used to this and so on. If you're grown up, you don't worry about it too much. And this really very easy is mainly a matter of saying homogeneous in the right place. Right, so I already said homogeneous here. Homogeneous in Korean is chechi. It's a word derived from Japanese, saiji. Right, so as I said, if I take these homogeneous coordinates, then the xi themselves are not functions here. The things that are functions are ratios of homogeneous polynomials of the same degree. So I'll get to this in a few weeks' time, and I hope I'll explain it better. Right? But as I will explain today, one aspect of this really very easy thing. So there's just a little trick you have to do to counter this equivalence relation, and then after that everything will be straightforward. Right? And 4, projective geometry is geometric. Right, so what I mean by this is when you do a course on algebraic geometry, you write down polynomial rings, you write down ideals of functions, ideals of polynomials in polynomial rings, and you prove finite generation theorems, and you prove Nash-Stellensatz and so on, and it is all algebra. Whereas the half of algebraic geometry is geometry, and I want to start doing the geometry straight away from the beginning. Right. So if you study affine algebraic varieties, so in a straightforward way you study subsets of affine space defined by polynomial equations, very soon you find that you're doing not geometry at all, but algebra, especially commutative algebra, some field theory as well, commutative algebra. So later on, of course, the algebra and the geometry are going to get mixed up anyway, so, but I want to start by talking about projective space. So this is some kind of motivation. I'm sorry if it's more confusing than it is useful. Okay. So let me now talk mostly about P2. And I want to take P2, I can write it P2 XYZ. So XYZ are the same as X0, X1, X2. Right? It's just that when you have a small number of variables, you really don't want to carry around these indices all the time. Right? So this is the picture that's still on the board there. When I draw this space, what I think is this. This is x equals 0, y equals 0, and z equals 0. So I have three coordinates, x, y, z. I'm talking about triples of elements in this field. So you can think of them as real numbers just for the moment if you want to, but I'm really thinking of complex numbers. Right? So let's think about these ratios, x to y to z. Right? So this is a ratio. I'm free to multiply by that lambda at any time. So think of the guys, think of the points with z not equal to 0. Right? So if z is not equal to 0, then this thing here is twiddles x over z, y over z to 1. Yes? So I told you what the equivalence relation is. I even told you how to pronounce it. Right? And I say I can multiply by any non-zero element in the field K. So if z is non-zero, then I can divide by it. Dividing by z is 1 over z is a non-zero element of the field, and I get this. And so I can call this as you know, x, y in K2. So you know, maybe I should use some different letters or something, but when you do calculations, you just say, well, I've got this guy 1. This last coordinate is always going to be 1, so I might as well just forget him. And so this is saying that if I take the P2 and I, just for the moment, I forget the points where z is 0, where the third coordinate z is 0, then I get something which is just the ordinary K2. So this piece of the diagram here is just the ordinary x and y plane. So this is the ordinary xy plane of coordinate geometry. Right. So I've got the fundamental object here is this ratio x to y to z, but if z is not equal to 0, I can just set z equal 1 and forget about z. Right? And then the only thing I've got is x and y. I've got, so, you know, so let me draw this picture which sort of explains a lot about the construction I made there. So the picture is this. Here is how am I going to use the blackboard? The picture is this. Here is K3, right? And so here is a coordinate system. X, Y, and Z. I'm drawing Cartesian coordinates in 3 space, right? And let's think about the plane Z equals 1. Yes? So I told you the projective space here, n is 2, this is 3 space divided out by this equivalence relation. It's also the same thing as one-dimensional vector subspaces of, in this case, K3. So a point of projective space is a one-dimensional vector space. So it's something, it's some line through the origin. Right? So a point of P2 is a line through the origin. Okay, so let's take this line, let's just follow it up till it hits Z equals 1. So this is the same construction as I'm saying over there. Because of this equivalence relation, we can always assume that Z is 1. So instead of taking the line here, instead of taking the line up to, a line in a vector space, instead of doing that, I can just take this single point. Right? Well, it's a well-defined point. This line meets the plane. Okay? So that's very good, except for the one sort of pathological case, the one unfortunate case where, so line through the origin in K3 meets the plane Z equals 1 in one point. Okay? So let me just say this is called a slice of the equivalence relation. Yes? So slice is what you do when you cut, take a large piece of beef and cut it up into bulgogi. So this means I've got an equivalence relation, and by drawing this plane here, what I can do is I can pick out one point in each equivalence class. Right? So this is very good when it works. It means I can throw away this complicated definition of projective space and just say this is the plane here, the plane Z equals 1 in K3, and that's the same as K2 with coordinates x and y. Right? And that's very good, except that it doesn't always work. So, except if the line is in the plane Z equals 0. Okay, so here's a line. Also, it's also one of these guys here in the definition of projective space, but it has the misfortune of lying completely in the xy plane, and therefore when you try to take its intersection with the plane Z equals 1, you get nothing. So I can't, in this case, there's no equivalence relation here, like this. So this is the phenomenon of parallelism. Parallelism. So lying in the plane has the property, is the same thing as saying that I'm parallel to this plane Z equals 1. So we're working in K3. K3 is, you can think of it, if you think of the real space is three-dimensional, then there's a, if I take the line of sight from my eye to the faraway horizon, then I'm doing something like this. I have a line and a plane, and they go on infinitely far away, and they never meet. They always stay that much apart. So I see this is, you can think of you can think of this in terms of perspective, right? So this line here, L, corresponds in some way to pencils of parallel lines. So in this case, so let me call this line L. This line L corresponds to a pencil of parallel lines in this K2 at Z equals 1. Right. And the thing I'm talking about there, when I'm talking about this extreme case of lines, these are points along here. So these are points, so to speak, on the horizon at infinity in the, so the points of P2 with Z equals 0 can be thought of as points at infinity in this K2. Right. So if we were committed always to working in K2, if we could only live in K2 and we weren't allowed to work in any other space, then we'd have to describe these points at infinity in some kind of way as pencils of parallel lines in the plane. And this is, this is familiar to people who take photographs and so on. There are points on the horizon which are not points of the real world. They're sort of imaginary points, and what they are is pencils of parallel lines. Right? So, as I said, this is geometric, and it does have some kind of intuition in it. It does have some kind of intuitive meaning to talk about points to infinity where parallel lines meet. However, technically speaking, it's really very, very inconvenient, because you'd have to start making every single argument you do is going to have except if one of your lines doesn't meet the plane in question. Right? So the whole advantage of projective spaces, so I told you what to do if Z is not equal to 0. But I could do exactly the same thing with X or with Y if X or Y was not equal to 0. So instead of having these kind of contortions about finding some, finding some kind of intuitive description of these points out at infinity, why don't I just, set up my measuring equipment, my camera and so on, in a place in a sensible way, so that I can actually see these points. So if I've got a point where Z is 0, then one of X or Y is not equal to 0, and I can just use that. So better when Z equals 0, forget about this model and work instead with, say, X not equal to 0 or Y not equal to 0. And I can do, of course, the same way. Then, for example, on this piece, then I've got X, Y, Z. Right? I can just say this is 1 Y over X, Z over X. And this is again a copy of the set of all of these is a copy of K2 with some I won't say Y primed or Z primed or Y double prime Z double primed or something as coordinates. Okay. So, you know, if I have to change coordinates going from this one to this one, I have some sort of messing around with how to write y over x as a function of x over y, and how to write z over x as a function of x over z and y over z. And, you know, it's sort of moderately messy, but it's basically a very simple calculation. And later on we'll see that we basically don't need to do these calculations. Okay. So I'm just talking about the definition here, and as you know, if you've got a child and you want the child to ride a bicycle, you don't spend 1 hour giving a lecture on the theory of the bicycle. Right? What you do is you put the kid on the bicycle and you say, right, off you go. And of course he falls off a few times. He or she falls off a few times. Okay, so I'm going to start applying this now to the theory of conics. So I'm now making contact more directly with the material of chapter 1 of UAG. So conics. So what I'm going to do is I'm going to take Q of x, y, z, a homogeneous quadratic polynomial, so homogeneous quadratic monomial means a linear combination of x squared, xy, y squared, xz, yz, z squared. Right, so it's a linear combination of those monomials. Yes, so quadratic you all know means degree 2. Homogeneous means it's a sum of things and all of the terms are of the same degree. So all the terms in it are of degree 2. So for example, if I write x squared plus y, this is not homogeneous. Okay, and so I've got my P2 here, and I want to take the curve given by q equals 0. I'm going to use notation like this. Right? So this is a set of, so I'm taking points in P2, and the points have coordinates x to y to z, such that this q here, q of x, y, z, equals 0. And I want to treat this as a curve. So there are 3 coordinates here. At any point I can forget one of the coordinates, as I've just explained to you, so there are really 2 coordinates, and then I'm writing down an equation in 2 coordinates. So the fact that this is homogeneous means that, well, I'll discuss this later in a lot more detail, but the fact that this is homogeneous means that this condition, q of x, y, z, does not depend on the choice of the representative of the equivalence class. If I multiply x, y, z through each by lambda, then the q gets multiplied through by lambda squared, and this condition, so the value of q changes, but whether or not it's 0 doesn't change. Right, so this is a well-defined condition on a point. So I want this q to be non-degenerate. And I want it to be non-empty. So example of something that's degenerate would be if I write down xy equals 0, this is degenerate. Or if I write down x squared plus y squared plus 1 equals 0, this is empty over the rails. Right? So I'm excluding these two cases. I'll explain non-degenerate in just a minute. So there's a theorem, very elementary, elegant little theorem, saying that given C in P2, non-degenerate, non-empty conic, then after a change of coordinates, C is, if I write here, you can't see. So after a change of coordinates, I can assume that this Q I'm writing down of x, y, z is, or maybe is proportional to, let me not worry too much about it, is given by x, z equals y squared. Sorry, xz minus y squared. So I start off with a polynomial here with 6 different coefficients, and I say I can mess around a bit. So after coordinate change and multiplying q by a scalar, then I get q is this xz minus y squared. Right? So I won't say this is the best conic. This is my favorite conic. I'll explain immediately different things I can do with this form. Okay, so first let's have non-degenerate. And I really don't want to go too much into this. Non-degenerate. I can write down 4 or 5 equivalent conditions. Say that quadratic form Q, quadratic form of rank 3. Right. So a quadratic form of rank 3, it means it's ax squared plus by squared plus cz squared, right, with a, b, c not equal to 0. Right, or equivalently, Q has bilinear form. The bilinear form is 1/2 of Q of x of E plus F minus Q of E minus Q of F. Right? So I'm cheating a little bit here. I'm assuming that characteristic of K is not equal to 2. So if you're pretending you don't know what a field is, then and you should only think of the field being the real numbers or the complex numbers, then you shouldn't be worried by this at all. Right? So if I've got a quadratic form, I can make a bilinear form out of it by doing this. This is essentially forgetting the straight quadratic terms and keeping the cross terms in this QE plus F. Right? So this is a bilinear form, is non-degenerate. Right? And so non-degenerate here means that it doesn't have a kernel, that a non-zero vector is paired with some non-zero vector. It is paired in a way, it's paired by Q. Anyway, I'm not going to explain it too much. Right? So the curve Q is non-singular, meaning that dq by dx or dq by dy or dq by dz is not zero at every point. Okay. So these are sort of positive properties. These are good, virtuous properties. Let's sort of exclude. Instead of that, let's sort of exclude the evil ones. So Q does not contain a line. Okay, so you can see that these are equivalent. So these conditions are equivalent. Right. So this is what I mean for my conic to be non-degenerate. I want it to be non-singular in any of these four senses, any of these four equivalent senses. It's not especially difficult to do this properly, but I'm just cutting corners a little. So why is this? I said a theorem there, and so it's my obligation to discuss a proof of it.